just have you read this without me having to say anything. So here's what I'd like you to do. I'd like everyone to read from the top where it says extrema down to where it says local or relative extreme values. So please read that like 2/3 of a page. And I guess somehow you and I are going to have to link this thing. You and me, Leila. Okay. Oh, have you read it yet? Are you done? I'll wait, because I think a few of you aren't done. Okay, hey, here's another example. Tell me, is there, for this function, is there an absolute minimum? No way. This guy just goes down farther and farther and farther, and any point I choose as the absolute minimum, well, there's going to be a point lower than that. So there is no absolute minimum. Is there an absolute maximum?
Yeah.
Sure. Well, what is the value of the absolute maximum? Good, f of p. And when they ask, find the absolute maximum, they're always going to ask, that's the y coordinate they want. The absolute maximum value is f of p. If they want to know where's the location of the absolute maximum, then you'd say at x equals p. You see? But the absolute maximum is the y value. Okay, great. Well, if my absolute maximum is f of p, what does that say for f of r? What would I call f of r? Do you remember the name we give for a guy who's the king of his own little hill? Even though he's not the king of the entire world, he's the king of his own little hill. Good. I mean, that ends up kind of looking like a vertex, but it's a special type of maximum, but it's not an absolute maximum. Yeah, it's a relative maximum or a local maximum, and we'll learn about that shortly. But I just want you to see, you got local maximum, absolute maximum, or relative maximum, because he's the king of his own little hill, okay? Well, we've got a situation where there's no absolute minimum, but could I change the domain so that there is an absolute minimum? Yeah. Sure, what would you like the domain to be, from what to what? Yeah, R to P. If I change my domain to be from R to P, if my domain is x is less than or equal to P but greater than or equal to R, now the only part of the curve I'm caring about is this part. You see? My domain now is a closed interval. It's not the open interval of all real numbers. And now I do have an absolute minimum. Let's say we called this, I don't know what to call it. Q, okay, we call this Q, then yeah, then I've got an absolute minimum, and the absolute minimum value is f of Q. Okay, great. Okay, but if I don't make this definition, then if my domain is all real numbers, then this guy wouldn't be an absolute minimum. What would it be?
Relative minimum?
Yeah, it'd be a relative minimum, because he's the, I don't know, the knave of his own valley or something. What's the opposite of king of the hill? I don't know, but he's the lowest part of his own little area. You know, that makes them a relative minimum. Okay? When you saw these guys here, what if I made my domain an open interval? Like, let's say my domain was x is less than, oops, x is less than p, but greater than or equal to r. Let's say that was my domain, so that now what I'm looking at is this. Okay? Could someone explain to me, why is there no absolute maximum?
Because you're infinitely closer to p.
Okay, good. It's like I'm getting infinitely closer to p. Someone else want to say it in a different way? Why is there no absolute maximum? Yes, Laura?
It's not differentiable.
What's that?
It's not differentiable.
No, that's not it. I mean, it is differentiable theoretically. Well, I mean, not at that point, because that point doesn't exist. But it's differentiable up to that point. Or let me just say this. I mean, what is it about this that makes it not have an absolute max?
It doesn't exist.
Yeah, it doesn't exist. Essentially, and I'll just give you my thinking, the Mr. Shana way of thinking about it. You know, any number you choose as the absolute max, you could always choose a number bigger. You know, because you get to be any number you want, except you can't actually be f of p. But you can get as close to f of p as you want, you know? So if someone said the absolute max, if someone said, well, I think the absolute max is f of p minus 0.0001, right? Where if f of p happened to be 3, then the absolute max for this guy would be 2.9999, right? But then someone else would come along and say, yeah, well, I think the absolute max is actually f of p minus 0.000001. That is, if f of p was 3, then my absolute max would be 2.999999. You see what I mean? And no one could ever choose an absolute max because someone could always get closer to f of p without actually hitting it. Okay, so you get this weird thing with open intervals. With open intervals, there's going to be quite often you're not going to get absolute maxes or absolute minimums with open intervals. Now there is an absolute minimum for that half open interval, and that would still be f of q. Okay, well, I think that's good. Okay, so now we're going to learn the extreme value theorem, but I just want to say again, like it says on my sheet, it applies only to closed intervals. You know, it is the absolute, the extreme value theorem doesn't apply to open or half open intervals. Okay, let me see what I want you to read now. Okay, read the rest of the page. So that'll take you like only a minute or so. Okay, so in layman's terms, like I say, he's just king of the hill. What they're saying is you get to be a relative maximum if someone can make a open interval where you are the absolute maximum of that open interval. Like this guy is a local maximum. Why? Because I can make an open interval like from there to there, such that he is the absolute maximum of that open interval. But like I said, just in layman's terms, if you think of it as being king of the hill or king of the valley, that's okay. Do me a favor and please turn the page over. look at that graph. I've given a graph that goes from A to B. And consider where you have your relative extrema. And I'm not going to count the relative extrema at the endpoints. I'm only looking at the interior points, not the endpoints. Like we said on the other part, you know, if you have a closed interval, then the endpoints of your closed interval will always be a relative extrema, you know? And I guess I should have said that, you know, a moment ago. But if I had a closed interval, let's say from A to B, and my domain is the closed interval from A to B, then the endpoints are always going to be a relative extremum. There's never any you know, exception. If you've got a closed interval, this guy's always going to be the lowest point of an open interval, which, by the way, there's nothing to the right, so I only have to consider from there to there. And yeah, he's the absolute minimum of that interval, and this guy's the absolute minimum of this interval. If I had a function that did this, like this, and this was an endpoint, then he's a relative max, okay? Because if I chose a half-open interval, because there's nothing to the right, he's the absolute max of that half-open interval. The point is, endpoints are always relative mins or relative maxes. There's no exception. Any question or problem on that? So if I were to give you a function on a closed interval and ask for all the relative mins and maxes, guaranteed. Okay, I'm trying to be so sensitive to your facial cues. But yeah, guaranteed, your endpoints are always going to be relative mins and maxes. But look at this graph here, and this is something that I'm sure you remember from Mrs. Lofgren. Look at the interior points at C, D, and E. What do you notice about F prime at those relative extrema? Yeah, they're zero, they don't exist. And so we get this definition of a critical point. And a critical point is a point x comma y such that f prime of x either equals 0 or f prime of x doesn't exist. Now, when you learned it with Mrs. Lofgren last year, almost all of the time when you guys encountered relative extrema, your f prime was equal to 0. I know what book she uses, and that book, for some reason, doesn't really spend a lot of time giving you f prime not existing. Almost all the time, f prime is equal to 0. And so, because f prime is equal to 0, that allows you to use something called the second derivative test. I don't know if this rings a bell with anyone, but to decide whether a point was a relative min or a relative max, you almost exclusively used the second derivative test last year. But you got to use the second derivative test only because 99.9% of the time when you guys encountered a relative min or a relative max, it had an f prime of 0 and not an f prime that's undefined. If f prime is undefined, you don't get to do second derivative test. You know what I mean? So I just want, that's probably the biggest thing I'm going to have to train you on, is to always be looking for points where f prime is undefined, because those are critical points as well. Okay? So now we get the extreme value theorem. Please read the extreme value theorem and the next line after it. The extreme value theorem says if you've got a closed interval, then guaranteed there's an absolute max and an absolute minimum on that closed interval. Guaranteed. I can't make a graph. You know, I can't make a graph on a closed interval where there isn't an absolute max and an absolute min. They have to exist. There has to be a biggest value, a y value, and a smallest y value when I have a graph on a closed interval. Now, there's two places for these absolute mins and maxes to exist. Where are these two places? What's one place that an absolute max or min could exist when you're on a closed interval? Sure, at the endpoints. For example, look here. My absolute min, is it at an endpoint or is it at an interior point?
Endpoint.
Endpoint right there, okay? So that's one place you must check to see if you've got an absolute minimum or maximum on a closed interval. You gotta check the endpoints. Where's the other type of point that you're gonna have an absolute min or a max? Good, an interior point, what's gonna be special about that interior point? What are we gonna call that point?
Relative maximum,
Good, good, and what do they call it like in here?
a critical point.
Yeah, it's gotta be at a critical point. So there's two places to look for absolute min and max. Either when you're on a closed interval, either the endpoints or at a critical point. If it's an interior point, it's gonna be at a critical point. If it's at the endpoints, then it's gonna be one of the endpoints. Okay, well, let's go ahead and do 4 examples together, and it will be fun. I'm gonna do example number 1, and then I'll have you guys do example number 2. So here comes example number 1. And I'll do it over here. Then you'll do example 3, then you'll do example 4, and then that's it, I'll be done. Then I can, in fact, I might just put your homework on the screen and let you do some projects. Here you go. Example number 1. I want to find the absolute minimum and maximum values for that function on that closed interval. Well, there's only 2 places the absolute mins and maxes can be, and that's either at critical points or endpoints. So we're going to find the critical points, and we're going to find the endpoint values. Let's do the critical points. To get the critical points, I'm going to take the first derivative. And then, remember, critical points, either the first derivative is 0 or undefined. So there's no, is there any value of x that makes the first derivative undefined? Not this time. I could give you problems where that happens, but not here. There's no value of x that makes the first derivative undefined. But there are values of x that make it 0. I'm going to factor 3 out, so I get x squared minus 4x plus 3 equals 0. So I get x minus 3 times x minus 1 equals 0. So I get my critical numbers, and that's something you may have learned last year. When it's just the x, for some crazy reason, they don't call it critical points because the point requires an x and a y. If it's just the x, they call it the critical numbers. So my critical numbers are at 3 and 1, which means I need to figure out what y of 3 is equal to and figure out what y of 1 is equal to. Y of 3 is 27, negative 27, 0. Y of 1 is 1 minus 6, which is negative 5 plus 9, which is 4. All righty. And now I'm going to look at the endpoints. I need to find what y of negative 1 is and what y of 4 is. Y of negative 1 is negative 1 minus 5, minus 6 makes negative 7, minus 9 makes negative 16, then 4, I get 64 minus 96, 64 minus 96 is negative 32, negative 32 plus 36 is 4. Great. You tell me, what's the absolute minimum value for this function on that closed interval from negative 1 to 4? The value.
All done.
So give me the x.
Negative 16.
How many people thinking negative 16? Yay, good for you guys. That's the absolute minimum value, negative 16, and it happens, you know, at x equal negative 1 if you're so inclined, but there's the absolute minimum value. Tell me, what's the absolute maximum value? And what is that value? 4. Happens in 2 places, but it's 4. That's the absolute maximum value, and it happens at x equals 1 and x equals 4. Okay, so hey, that's good. So this is the process you're gonna go through. If someone asks you for an absolute min or absolute maximum value on a closed interval, you're gonna look at the endpoints, you're gonna look at the critical points. And so what might happen is I might give you an equation that tells you the profit. This equation models the profit that your company makes. You want to maximize your profit. And there's a closed interval. This is how many widgets you can create from this amount to that amount. Well, you're gonna take the first derivative, look at the critical points, look at the endpoints, and that'll make your decision as to how many widgets you should make. I don't know if any of that made sense, but anyway, that's where you look, endpoints and critical points. So I'd like everyone to please do example number 2 now. Alrighty, hey, let's take a look at this one. So here comes example number 2. Y equals x to the 2/3 power on the closed interval from -2 to 3. So first I'm gonna look at the critical points, and I'm gonna look at the endpoints. Okay, I'll do the endpoints first this time. I need to find y of -2, which is going to be the cube root of 4, which is whatever the heck that is. I don't, did anyone decimalize the cube root of 4? What is it? You didn't? Anyone know what the cube root of 4 is? Like 1 point something?
1.587.
Thank you very much. 1.587. Okay, and then we got y of 3, which is going to be the cube root of 9. And did anyone get what the cube root of 9 is?
2.08.
Say again?
2.08.
Okay, 2.08. Good. Now let's go ahead and get our critical points. I got y prime equals 2/3 x to the -1/3 power, which is the same as 2/3 times the cube root of x. All right. So is there a value of x that makes that equal to 0? No, 0 doesn't make it 0. What does 0 make it? Yeah, undefined, and that's okay. right? I've got a critical point, critical number at x equals 0 because y prime of 0 is undefined. So you'll notice I don't have any points, I don't have any critical points where the slope of the tangent is equal to 0, but I do have a critical point where the slope of the tangent is undefined. And so let's go ahead and find what y of 0 is. Y of 0 equals 0. Alrighty, so what's the absolute minimum on this interval? Absolute minimum value?
0.
Yeah, I got my absolute minimum value is a 0. Okay, and what's the absolute maximum? 2.0. Thank you. Yeah. So that's all there is to this. You just check the critical points, check the endpoints, and whoever's biggest gets to be absolute max, and whoever's smallest gets to be absolute min. You know, but the extreme value theorem assures me that I will find them. So I'd like everyone to please do example number 3 now. And by the way, you'll notice example 3 is defined piecewise. And what's always your go-to when you have a piecewise defined function? What should you do?
Graph it.
Yeah, graph it. Graphing piecewise functions is always an incredibly good idea. Number one, make sure that it's continuous. And number 2, you get to look at what you're looking at, you know? So go ahead and graph number 3 and then find the relative min or max. So I'm not asking for absolute min or max, I'm just asking for relative min or max. And you're gonna have to graph it. Everyone's here today. Yay.
Thank you. Once you graph it, is there really any reason for me to take a first derivative and look for critical numbers? I mean, it's pretty darn obvious, right? I want to remind you, if someone gives you a piecewise defined function, one place for sure that you should always look for a relative min or max is going to be at that border point. Because it's very rare that a piecewise defined function is differentiable at the border point. It's almost always a corner point. So you guys okay that you got a relative max at x equals, what does it say, find min max? Yeah, so I got a relative max of 5 at x equals 0, and I got a relative min of 3 at x equal 1. How many people got that? Okay, good, yeah, and it's okay. And it's as easy as graphing. I mean, yeah, you could have taken the first derivative. You could have taken this guy and, you know, get an expression for f prime of x, which would be negative 4x for x less than or equal to 1, and 1 for x greater than 1. So there's not going to be any relative mins or maxes on this part of the domain, because there's no values that make f prime 0. But you're going to get a relative min or max at x equals 0, you know. So you could do it that way, but shoot, I would prefer that you just graph it. So there's one more thing I want you to do, and I want you to do this entirely graphically. In fact, do it on your graphing calculator. Look at example number 4. Go ahead and just do example 4 on your graphing calculator. And tell me if you can get the extreme values. Here's example number 4. Gotta give the function idea. Do I say what the domain is? No, just all real numbers, huh? Let's go like -3 to 3.
Mr. Shane,
Yeah.
do you want this or should I put it somewhere else?
What's that?
The test.
Oh, I'll take it. Wow, you're fast. You've done already?
Yeah.
Good for you. Am I getting an absolute min?
It's undefined.
Yeah, I mean, that's going down as low as I want, right? If I stick a 0 in for x, I get 0/1, but the log natural of 0/1 is -infinity. So there's no absolute minimum. That's freaky. Why did I even put that problem on there? Yeah, it just gets lower and lower the more I pinch the domain. Are you guys getting that there's no absolute minimum? Because if I put x equals 0, I'm taking the log natural of 0, and that's -infinity. I mean, the closer this quantity gets to 0, the more the negative the log natural of that quantity is. So there's no absolute minimum. Is there an absolute max? What if I let x go to infinity? Then I've got infinity over infinity squared, which is 1 over infinity, which is 0. Wow. Like, so when x goes to infinity, it's got to go to infinity. Here, it's a second, -20 to 20. Okay. And then, so it looks like there's an actual relative max, though, or an absolute max. do you notice that there's an absolute max? There's no absolute min, because when I get to 0, it goes, here, I gotta turn off my stupid phone. I'm sure it's a telemarketer.
Answer me.
Hi, have you considered solar panels?
They always ask me about government surveys.
Oh, really?
Yeah.
Yeah, I would prefer that. I always just get people who want to sell me stuff. Wow, good for you, government surveys. So what do you think, what sort of job is Donald Trump doing?
I don't know, usually just hang out when he's underage.
I don't know why I assigned this problem, but it looks like there's a relative max right there, right?
Well, there's 2.
Yeah, 2 relative maxes. Oh, let's find them. Left bound, like 0.1. Right bound, 2. Guess, I don't know, 1.5. So at x equal 1, I got my max. X equal 1. All right. So there's my absolute maximum value. It looks like negative 0.693. I think that if my memory serves, that's 1 over e. And it's happening at 1. And also happens at negative 1. So that's the sort, I guess I just wanted you to fiddle around with your calculator on this problem. How interesting. Yeah. Yeah, so you've got an absolute max at x equal 1, and that is negative 0.693. Could I do that using derivatives? I should be able to do that using derivatives. Hey, could you guys do me a favor? Take the derivative and see if you can find the critical numbers.
Is there a difference in taking the derivative of the absolute value of that number, or is it basically the same?
No, there is something you must do. Oh my God, who did I just kick? Sorry, Omar. I'm sorry I kicked your gigantically huge feet. I'm just kidding, your feet aren't that big.
It's not the only thing.
Mine are big. I bought them last year. I'm hoping they can last me for the rest of my teaching career.
How long do you plan to keep teaching for?
About 10 years. So I'll have to clean these occasionally. I had my other shoes, they lasted me like 5 years, the ones that were blue. Was I anyone's teacher when I had my shoes that were blue? I don't know if there's anyone in here. They were white, but they were actually blue, like Nike had blue shoes and then they stained them white. And then I bought them as white shoes, but as I wore them, they started to turn blue because they were actually blue with white dye on them.
Really?
Yeah, it was really freaky. Yeah. So I have blue, white shoes. Okay.
Huh.
You guys, this is what I need to have you see. I guess maybe this is why I put this problem on here. I'm really not sure why. I know I had a good reason when I did it. But when you've got an absolute value and you want to do calculus on an absolute value, you must always turn it in. Where's Daniel? Daniel, you must always turn it into a piecewise defined function. Okay? Because the biggest thing about absolute value is the absolute value of x equals x for x greater than or equal to 0, and the absolute value of x equals negative x for x less than 0. That's the definition of an absolute value. It says whatever you're taking the absolute value of, if it's positive, then you just don't change it. But if it's negative, then you've got to get the opposite of it. And so that's what I would have to do here. I'd have to rewrite this as a piecewise defined function where this becomes the log natural of x over 1 plus x squared for x greater than 0. And x can't be equal to 0. 0 is not part of the domain, so I don't get to let it be equal to 0. But do you see that if x is greater than 0, the thing inside the absolute value symbol is always positive, and so that absolute value is of no importance? Whereas if x is less than 0, like -2 or -5, since the denominator is always positive, the absolute value will just multiply it by -1. So you end up with log natural of negative x over 1 plus x squared. You see it? And that's what this function is. Whenever someone gives you absolute value redefined as a piecewise defined function, then you can go ahead and deal with it. So now what I'd like you guys to do in the next 2 minutes, go ahead and take the derivative of this guy and set it equal to 0 or set it equal to undefined, although really you'll just set it equal to 0. Take the first derivative of this guy, set it equal to 0, and see if you can find that critical number that I found graphically at 1 comma negative 0.693. Just curious to see if you guys can pull this off. Does everyone understand? What I'm asking you to do is essentially just work with this guy. Work with the right half of the function. Get the derivative and set it equal to 0. And at this point, I'll say good luck. I'll give you a couple of minute head start, then I'll do it. If you want to check your answer, when you take the derivative, it should be the reciprocal of that times the derivative of that. And that's what I got, and then I simplified it, and now I'm getting my critical numbers. Hey, have you guys successfully got the first derivative of that log natural? And then are you okay that if I want this fraction to have a value of 0, that means the numerator has to have a value of 0. The only way a fraction can have a value of 0 is if the numerator is 0 and x plus or minus 1 gets me that. So those are my critical numbers that make f prime 0. I've also got a critical number that makes f prime undefined, but it's not part of the domain. I can't plug 0 into the original function, so I don't have to concern myself with x equals 0 being a critical number because it's not in the domain. So that's how I would have found plus or minus 1. And then I would just stick 1 into the original function, and I'd get the log natural of 1 over 2, the log natural of a half, and that'll get me negative 0.693. You know? So yeah, you could have done this completely analytically, but I think doing it graphically is a lot easier. Alrighty, well, you know, this was kind of a meandering lesson, but let me just remind you of stuff. First of all, the extreme value theorem. What kind of interval does the extreme value theorem apply to? Good, closed intervals. And what does the extreme value theorem assure me of?
There is a max and there is a min.
Thank you very much, Daniel. And let me ask you another question. Where are the two places I'm going to look for these absolute mins and maxes?
Endpoints or at the
Good. Endpoints or at relative mins or maxes on the interior. Great. And then finally, what's true about the first derivative at a critical point? What's the first derivative equal to at a critical point?
equal to 0.
Good. 0 or what else?
Undefined.
Undefined. Okay, well, I think you'll be fine. I mean, tonight's homework is just this sort of thing. I don't know. We'll see how you like it. Good luck, you guys.